All right. So this week is test week. Make sure that you get scheduled to go out and take the test. We are jumping into chapter something. I don't know what we're doing next year. Let's see what we're doing next. Wow, that's really zoomed in. That's craziness. How do I zoom out again? There we go. That's better. So we are going into fluids. We're going to try to cover 2 chapters this week, 11 and 12. And then we'll try to cover 2 chapters next week, 13 and 16-ish, 16, 17. Try to see how much we can cover very quickly here. So fluids today is where we're starting. So let's get started. Can everybody see my textbook there?
Yeah, I can see it.
Excellent. All right, so fluid statics. This is essentially the study of fluids that aren't moving. That's why it's called fluid statics instead of fluid dynamics. And we're going to start off with some basic ideas of what a fluid is, some basic properties of fluids, and then we'll move on to some of the interesting things that happen with fluids. It's a fairly long section, 9 or chapter 9 sections, but I think we should be able to get through it pretty quickly. So first of all, what is a fluid? We start by talking about the 3 states of matter that you've talked about in many classes: solid versus liquid versus gas. And the real difference, between these 3 things is the internal structure or the microcosmic structure of these different states of matter. There are more states of matter than this, besides solid, liquid, and gas. What other states of matter has anybody heard of? Anybody heard of any other states of matter? No, anybody heard of plasma, for example? They've got plasma listed up here. So the plasma state of matter is a state of matter that's kind of like a gas, it's usually a gas that has so much energy in it that some of the electrons in the gas have been stripped off of the atoms. So you don't only have a gas, but you have charged particles flying around. And the flames in your fireplace are a plasma, for example. But there are other states of matter. There are superfluids. There's such a thing called a Bose-Einstein condensate, which is kind of the other end of the spectrum, very, very low energy, extremely low energy state of matter, where things are getting very close to the absolute 0 point of temperature. That's where a Bose-Einstein condensate can exist. So there are many different states of matter, but these 3 basic ones are the ones that we encounter every day. We encounter plasmas a fair amount as well. The microcosmic structure of a solid is it's very structured. It's got a lot of structure to it. There are a lot of forces holding things together. There's a lot of organization in a solid. Sometimes the solid has extremely organized structure that kind of has this kind of crystalline shapes going on, like these squares that are here. These red things would represent atoms. The springy things would represent the forces or the bonds between atoms. And sometimes it's very simple, like squares, and sometimes it's more complex, like dodecahedrons or something. But usually solids have these very strong bonds between things, and they can be atoms or molecules or a mixture of things inside the solid. It's usually not, set to one particular thing, but this very strong interparticle bonding is what creates that solid feel of the object. That's why you can't put your hand through it, because the bonds are so strong that your hand can't penetrate those bonds. the electrons on your hand can't slip in between those bonds without being repelled by those bonds. And so solids are solid. Right? Liquids have a much freer structure microcosmically. As if you were able to look in very close, you would see very weak bonds. The bonds are there, but very weak bonds between particles, which allows your hand to go into the liquid or whatever. It also requires that the liquid be bound by some barrier of some kind, like a bottle or a can or a bowl or whatever it is. And gases are even freer still, where there's almost no interaction between the particles. The particles almost never interact. They have almost no forces between them, and they're just kind of flying around doing their own things. And we live in a gaseous environment. There's gas all around us. The atmosphere is full of gas. We have gas in our lungs. So gases are very free, very little or no bonding, no forces between the particles. Therefore, it's much harder to contain them. Things that contain gases they're designed to contain gases have to be very sealed up. They have to be quite. They have to have quite enclosed, I suppose you could say, requiring all kinds of special sealing materials and sealing techniques and so on to contain gas. Those three things are very common in our lives, quite readily available, observable all around us. The two things in here that are fluids pretty much all the time would be liquids and gases. Fluid because they can move. They move without any trouble. They adapt to different containers that they're in. Gravity pulls on them really easily and changes their shape as it does that. As they do that, they flow, right? A solid, when gravity pulls on it, doesn't flow. It doesn't change its shape very much. There are some things that are solid that are kind of fluid. They're semi-fluidic. For example, glass. If you look at a window of an old church in Europe, for example, you have these churches that are 1,000 years old, 500 years old, whatever, and they have these huge stained glass windows. At the top of the stained glass window, it's the glass is really quite thin. At the bottom, it's really quite thick, and that wasn't by design. That wasn't on purpose. It's because the glass has been flowing over those hundreds of years towards the bottom. It actually makes the windows very weak at the top, and it's caused a bit of a problem. Many of these stained glass windows have had to be, excuse me, encased in other glass or even have pieces replaced so that they don't shatter. And many of them have shattered. It just doesn't take much to shatter a glass that's really thin at the top. But the fluids are things that generally flow easily without much trouble, without much resistance to that flow. And so that's what we're going to be talking about are the fluids. When we're talking about materials in general, we often talk about their density. To calculate or to define, excuse me, the density of a substance, you need to know the mass of that substance and how much volume it is occupying at that time. And you divide the mass by the volume to get the density. This letter here we use for density, that's rho, R-H-O, rho for density. And here are some densities of some different things. You have aluminum that has a density of 2.7 grams per milliliter. Water, 1 gram per milliliter. So aluminum is more dense than water. Air is 1 times 10 to the minus 3, or 1 milligram per milliliter, or 1 milligram per milliliter. These, you can also use these for kilograms, thousands of kilograms per meter cubed as well. More brass is more dense, copper is more dense, gold is more dense. You get all the way up here to tungsten. Tungsten and gold are very dense. Uranium also quite dense. These numbers are a little bit variable because there are certain types, for example, there are certain types of uranium that are more dense than this, quite a bit more dense than this actually. The different elements have different, what um, we call them isotopes is what we call them. So different isotopes have different amounts of neutrons and they have different densities. Liquids, you can see here, we have 1 gram per milliliter. A milliliter is 1 centimeter cubed. So it's like a box, 1 centimeter on each side, in case you're wondering. Blood, 1.05, slightly more dense than water. Seawater, also slightly more dense than water. Mercury, much more dense. Mercury is the only element, the only elemental metal in nature that exists as a liquid. And so liquid mercury, quite dense. Ethyl alcohol, less dense than water. Petrol, which is what gasoline is. Glycerin, which is kind of like what dish soap is made of. Olive oil, 0.92. And here you have all your gases that are all 10 to the minus 3, 10 to the minus 3. They're all in milligrams per milliliter. So very, very small densities for gases. Incidentally, the smallest, the lowest density solid is actually not much more dense than air. The lowest density solid is a material called aerogel. Aerogel was invented at a laboratory in my hometown, actually, the laboratory my father worked at. And it was invented while he was working there. He brought home some for me one day, and we played around with it. But this shows a piece of aerogel being held up by a flame. The flame is actually holding up the aerogel, and it has a flower on top of it. So the aerogel is protecting the flower because it has this property of protecting things from heat. And it also is very, very low density. It has this extreme low density that allows the flame to actually hold it up along with the flower. So there are many different types of aerogel, many kinds of aerogel, but the lowest density aerogel that I had was only about 10 times more dense than air. So it was if you breathed on it, it actually would float up into the air and float away. It would be very difficult to contain it, to hold on to it. But it's extremely strong for its density. It's such a low density, but quite strong for that low density. Here you can see a piece of aerogel being held up just by the stamina of this flower. The flower stamina being very delicate and not being affected by the weight of the aerogel. So aerogel is a very interesting substance. They made it by infusing plastic with air bubbles while it's being heated up. So it's quite an interesting. It's used for all kinds of things, many different things. But that's density for you. And here you have a nice demonstration of density. Here we have a ton of feathers and a ton of bricks. They have the same mass. So if you put them on this, if you balance them, on this seesaw, they will balance out. But the feathers take up far more volume, right? Far more volume. Here we calculate the mass of a reservoir from its volume. We know that a reservoir has a surface area of 50 kilometers squared and an average depth of 40 meters. We want to calculate the mass behind the dam from the density. The density of water is mass over volume. We can figure out the volume from the stuff they told us, and we know the density of water, so we should be able to solve for the mass of the water. The volume of the reservoir is going to be the area times the height, and we've got the average depth to be 40 and the area to be 50 kilometers squared. We have to convert this 50 kilometers squared into meters squared, which they do. They don't do it explicitly, but they do it. Oh no, they do it explicitly. Here's the explicit conversion. There's 10 to the 3 meters per kilometer. So you take this 50, you multiply it by 10 to the 3 squared, so that's by 10 to the 6, and then you multiply by 40, and then you get 2 times 10 to the 9 meters cubed, so 2 billion cubic meters of water in this reservoir. Well, that's our volume. We plug that volume in to solve for the mass. by multiplying the density of water by the volume of the water, and we get the mass of the water. 2 times 10 to the 12 kilograms. It's a lot of water. It's a huge mass of water. So the next thing we want to talk about is pressure, because when you have a large volume spread out over a surface area of a fluid, because fluids don't come up and just poke you, right? If somebody comes up and pushes you, they're pushing you at a fairly specific spot on your person. But fluid is always pushing on us, but all over our body at the same time. The fluid that is the atmosphere is pushing on our feet, and it's pushing on our legs, and pushing on our chest, and it's pushing on our side of our head, on our hair. It's pushing on us from all directions. So it doesn't make sense to try to calculate that in terms of forces, because it's so many different forces at so many different places. It's just not practical. So what we talk about pressure. The pressure is the amount of force spread over an entire area. So the total force over the total area. And so pressure is a much more practical thing when we're dealing with fluids, because that's how fluids behave. They spread themselves out over some area and do some pushing that way. Pressure, being force per area, or force divided by area, is going to be newtons per meter squared, and we're going to give that a name. We're going to call that 1 Pascal. So 1 Newton spread over 1 meter squared is 1 Pascal of pressure, named after a Frenchman named Pascal. And there are other units used for pressure pretty commonly in the United States that you need to be aware of. You will likely see these different units in the United States if you're working in medicine or engineering or something like that, chemistry of any kind. So the bar, you have 100 millibar, which is equal to 1 times 10 to the 4 Pascal. So it's 100 millibar is equal to 10,000 Pascal. So the Pascal is actually a fairly small unit of measure. There's also pounds per square inch, which you often hear, or PSI, pounds per square inch, PSI. I don't remember what the conversion is for PSI. But there's also millimeters of mercury that's used in blood pressure. So millimeters of mercury comes from the idea of something we call a manometer, which we'll learn about later. That's mmHg. If you're in the medical profession, millimeters of mercury is often used. Let's do some calculations of pressure just for fun. If you're working outside the International Space Station, the atmospheric pressure is pretty much zero. There's no atmosphere out there to speak of, very little atmosphere. And so nothing's really pushing on your body when you're outside this International Space Station. The air tank of this astronaut that's working outside is reading 6.9 times 10 to the 6, or 6.9 million pascals of pressure. So there's that much pressure inside the tank. What does this look like? This looks like this. Here's the tank. And you've got all this force pressing on the inside of the tank, all this gas pushing on the inside of the tank. And if you take all this force that's pushing on the inside of the tank and divide it by the total area of the tank, you will get however much pressure there is pushing on the inside of the tank. And that pressure is going to equal force divided by area, of course. That's how you define pressure. And they've told us what that pressure is. So there's the pressure. That's our P. Now we've got the area. We can figure out the area because they tell us it's a cylindrical tank, which means it's got circles on the top and the bottom, and it's got this height to it. And so the volume is going to equal the area of this circle right here times the height of the tank. Well, the area of the circle is going to equal the radius of the circle squared times pi. And the radius of the circle squared, they tell us the diameter of it right there. So that radius is going to equal that diameter divided by 2. So they divide that diameter by 2 right there, and they square it. That's the r squared. They multiply by pi. They multiply by the height, oh no, so sorry, the height of it is, oh, they actually only want to know the force on the flat end of the cylindrical tank. So we're only looking at this area here, not the whole area. So then we don't want to know the volume anyway. We want to know the area. So the volume is the circumference times the height. But we don't need to know the height because we only want to know the area of this disc because that's the one they want to know. They want to know the pressure or the force on the flat end. So we're only looking at the pressure on this end of the tank. So once we've got that area calculated, then we're done. There's the area calculated right there. Then we multiply it by the pressure to get the force after we've solved that equation for force, and we get the amount of force. It turns out to be 122,000 newtons, a fair amount of force spread across that area. If you calculated it for the whole tank, it would be even more. It would be even more force because there's more area that you're including. For the whole tank, it would be this area on the flat end, plus another one for the bottom, plus the area of the cylinder. The area of the cylinder is the circumference of that, which is 2 times pi times r, circumference of the circle at the top, times the height of the tank. That's the one I was thinking of before, but I did it wrong. But anyway, they do that there, and we can calculate that pretty quickly. Here they get that 100,000 newtons-ish. Here's a tire that has pressure, high pressure air inside it. Why would we want high pressure air inside? Well, because what's really happening here is that there is pressure on the outside as well. The atmosphere is pressing on the tire from the outside. The air from the atmosphere is pressing on the outside. And it's doing it from both sides. It's doing it inside this as well. And it's even coming from the side. And all this pressure that's pushing on the tire from the outside and all the pressure that's pushing on the tire on the inside are pushing against each other. So if you want to use this tire to roll down the road, which pressure do you want to be higher? The outside pressure or the inside pressure? Anyone? Which one should be the higher pressure? The outside pressure or the inside pressure? Come on, somebody give me a guess. Should we turn it into a quiz?
The outside pressure?
You want the outside pressure to be bigger? Does anybody agree or disagree?
Yeah, I think the outside pressure.
Okay, well, let's think about this. Let's just look at one wall here. Where this is the, whoops, let's clear that. Clear. So let's think about one wall of this. So we're zooming in right here. This is just the wall of the tire. Now, the pink side is the inside of the tire and the white is the outside of the tire. So I've got big pressure on the outside and little pressure on the inside. What's going to happen in this situation if you have a big force going this way and a small force going this way? What's going to happen to the tire? Are those forces balanced?
No.
They're not. So which way is the total force going to be pointing? Towards the tire, right? This is going to be my total force after I add these two together. Well, that's going to make the tire accelerate this way. That's the same as getting a flat tire. That squeezes the tire. So do we want a flat tire? We don't really, right? So if the pressure outside the tire is bigger, it crushes the tire. So that actually is not correct. We actually would like to have a pressure inside that's greater than outside. So if these represent our outside pressures, then we want a smaller pressure outside. So we want more pressure on the inside than the outside so that the tire is being pushed out all the time and it's staying inflated all the time. The other thing that it does is that where we put the air in here at the stem, that increased pressure on the inside compared to the outside keeps the air from escaping because the inside pressure is sealing this valve here so that the air can't get out. So the high pressure actually keeps the air in the tire. They put a spring in there too to prevent that air from coming out there. But in truth, you do want more pressure inside the tire than out rather than outside in to prevent the tire from flattening. Here's a swimmer underwater. We have a swimmer, and all these arrows represent forces of the water on the swimmer. And you notice that below the swimmer, you have bigger forces than above the swimmer. And so what does that do to this swimmer? Well, that's going to make the swimmer, if you add this force to this force, you get a total upward force. All these are going to be total upward forces. And you're going to get a swimmer that floats in the water rather than one that sinks, right? And for every human, there is a point where you go underwater and you float. You don't necessarily float on the top. Not everybody floats on the top of water, but you usually float, some people will float a little further down than others. And that's because of these unbalanced forces. It turns out that the deeper you go underwater, the more pressure there is, which means there are more forces. So at the bottom of your body, there are more forces than at the top of your body. So you will float. And this is what we're going to talk about next, is the difference of pressure when it comes to height. Why does depth, going deeper into a fluid, make more pressure? That's because the pressure that we're feeling when we're going underwater or we're in the atmosphere or something, the pressure that we're feeling is actually the weight of the fluid above us. So imagine that you're in a pool like this swimmer in the previous section, and you're swimming along. The top of the back of this swimmer, which is the top of the swimmer here, that part of his body is only feeling the weight from this water here. The water that's above his back is pushing on his back because it's trying to go down because gravity is pulling it down. So gravity is pulling that water down and it's running into the swimmer's back, and all these arrows represent the weight of that water. However, if you're at the bottom of the swimmer's body, the bottom of the swimmer's body is feeling the weight of all the water down to there. So any water that is between the top and the bottom is also added to the weight of the water here. And that the funny thing about water, fluids in general, is that if you push on one end of the fluid, that fluid that you pushed on pushes on the next bit of fluid, pushes on the next bit of fluid, and it propagates throughout the fluid. And it actually will start pushing in every direction. It doesn't care if you started pushing left, it'll push up and down and sideways and whatever else, because it's free to move around. It's free to kind of adapt and flow. So even though the weight of gravity is pulling this water down here, the result will be that it will actually push up on the swimmer because of that those fluid dynamic, those fluid issues, the properties of fluids. This is a principle called, I think it's actually called Pascal's principle. I think Pascal is the one that figured out this principle that if you push on a fluid in one place and create a pressure in that fluid, that pressure propagates throughout the fluid. So the bottom of the swimmer has more pressure on it than the top, or more force on it than the top of the swimmer. So the weight of the water is equal to the mass of the water times the gravitational pull. Well, the mass of the water is going to be determined by the density of the water times the volume. And the volume is determined by the area, the cross-sectional area times the height of the water. Or it doesn't even have to be water, it can be air. This is the same reason we feel pressure on the earth, is because of the air above us. The weight of the air above us creates pressure all around our bodies. Our bodies are designed to withstand that pressure, so we don't really feel it per se. We're used to it, in other words. But if you get in an airplane and you go up high in the airplane, that pressure goes down as you go up because there's less air above you, and your ears start to swell because they're used to having more pressure on them. So this is what it looks like with your ears. Your ears essentially have your ear canal essentially ends with a big rubber-like drum on it called your eardrum. And it's a stretchy thing here. It's a stretchy thing. Inside your ear, there's this fluid, and it has a certain pressure in it that is equal to the pressure of the air outside. So there's this pressure pushing on your eardrum this way, and the air outside has an equal pressure pushing this way, so that your eardrum kind of just stays relaxed there. When sound comes by, it creates more pressure, and it makes the eardrum wiggle, which hits some bones back here, which hits a nerve, and that's how you hear. When you go up in a plane, the pressure outside becomes much, much smaller. And so the pressure inside starts to stretch that membrane out, and it starts to hurt your ears. And so you yawn. When you yawn, it actually changes the pressure inside here. If you go to the end of your eardrum, there's this big whirly-gig thing it's like a tank of fluid that can remove fluid or increase fluid in this area. So it can increase the pressure by putting more fluid in, or it can decrease the pressure by taking more fluid out. So when you go up high in the plane and you yawn, it takes out some fluid, and it reduces the pressure inside, and so that your ears feel better again. And when you go down in the plane, you yawn again, or you chew gum or something, and that triggers this reservoir of fluid here to increase the pressure as it goes down. Because as you're going down, there's more fluid above your head. There's more of the atmosphere above your head pushing on your eardrums. And then when you're going down, you have a big pressure outside and a little pressure inside, and it pushes your eardrum inward, and it hurts again. What you really want is your eardrum to be nice and relaxed right in the middle. Anything inward or outward hurts. And you can press hard enough to rip the eardrum. If you rip your eardrum, you'll bleed out your ear, and it'll be very, very uncomfortable. And it may not heal if you rip it bad enough. So you got to be careful listening to really loud sounds or experiencing very extreme differences in pressure. Got to be careful with that. Your ears. Okay, let's see here. So we say that mass is equal to the density of the fluid times the volume of the fluid. The volume is equal to the area, the cross-sectional area times the height of the fluid. That's how high you are, how high the fluid is above you, essentially. How much height and fluid there is above you. And then the area, the mass then is going to equal the rho times this volume. So rho times area times height there. And then you plug that back into the pressure equation for the mass, and you get it rho times area times height times gravity divided by area. Well, that's the same area, so they cancel out. And you just get the height times the density times the gravity. And it doesn't even matter how big of an area it is. And this is true for pretty much any situation. So if you want to know what the pressure is of the air above your head, you need to know the density of the air above your head, the height of the air above your head, and gravity, which is of course 9.8. Here we can do lots of different examples with this. Here we want to calculate the force that a dam has to hold back. How strong do you have to make this dam? What's the biggest force it has to hold? Well, we already calculated what did we calculate before? The mass of water in a dam or something like that. So yeah, it says right here, I wasn't reading. So we calculated the mass of water. So we know we can actually calculate the weight of the water as well if we need to, but we can also calculate how much pressure is acting there, because pressure is equal to the height times the density times gravity. Well, they've told us here that the dam is 500 meters wide and it's 80 meters deep. So the 80 meters deep is the height of the dam, right? So that's the H right there. We know the density of water, we know gravity, so we know we can calculate the pressure. The pressure behind this dam is, for an average depth of 40 meters, is going to be 3.92 times 10 to the fifth, or 392,000 Pascal, 392 kilopascal. So that's how much pressure on average is going to be on the back of the dam that we're dealing with. We know that force is equal to pressure times acceleration from our definition of pressure. So we can calculate the average force if we know the area of the dam. Well, we know the width of the dam and the height of the dam, so we can calculate the area of the dam. We do that, the average force is 1.57 times 10 to the 10 newtons. And that seems like a big number, but remember that the mass of the water was 1.96 times 10 to the 12. And the weight of the water was 1.96 times 10 to the 13. So the mass and the weight of the water are much bigger than this. The weight is 1,000 times more than this. So you don't have to build a dam that can hold the entire weight of the water back. You can build a dam that holds 1,000 times less than the weight of the water and still hold the water back. The problem is that the pressure isn't constant down the dam. At the top of the reservoir, the pressure is different than at the bottom of the reservoir because of the height. Remember, the height matters. So at the top, you have less weight of water pressing on the dam. At the bottom, you have more water because it's higher. So dams are built usually in a parabolic form or a wedge kind of form, where the bottom is much wider than the top. And you can see that in all kinds of dams. You can just go up to the dam here at Lake McConaughey, not McConaughey, Lake Maloney here in North Platte. And you can see a big rock and gravel and dirt dam that's just wide at the base and skinny at the top. If you go to McConaughey, you can see a much bigger dam like that as well, made in the same fashion. It's much wider at the bottom than it is at the top. Or you can go to a very engineered type dam like the dam on Lake Mead or something like that, big concrete dam. And it's the same kind of thing. At the bottom, it's a lot of concrete. In fact, some of the dams that were built 100 years ago are so thick at the bottom, the concrete is so thick at the bottom that the concrete in the middle is still not dry, still not cured even 100 years later. And it's not expected to be cured for another 100 years. So that's some interesting things about that. It turns out that the amount of pressure that we feel from the atmosphere, from all the air above our heads pressing down on our heads, is actually about the same as the amount of pressure that is felt at the bottom of the dam here. At the bottom of the dam here, we calculated 1.57 for pressure. We had, where did the pressure go? Here's the pressure. Where did the pressure go? That's the force. Oh, here it is. So here's the pressure at the bottom. It is the average pressure across the dam, 392 kilopascal. So 392,000 Pascal. That's the average pressure across the dam. And the pressure that we feel from the atmosphere is 100,000 newtons. Instead of 300 or 400,000 newtons, it's 100. So it's only about 1/5 of the pressure that's felt across the dam on average, but it's not that much different. We're just used to feeling this. The thing that we don't tell you here in this particular situation is that at the deepest part of the dam, you have much more pressure than the average across the dam. So that's different. And also the air above this water also pushes on this water and adds its pressure to this pressure. So whatever pressure that you have at the bottom of the dam here, 400 kilopascal, you also have to add the 100,000 Pascal or the 100 kilopascal from the air above it. So the actual pressure at the bottom, because of the water plus the atmosphere above it, is equal to this pressure, which is this pressure from the water, 392 kilopascal, plus this pressure from the atmosphere above it, because the atmosphere also pushes down on the water and increases that pressure. So here they're showing this idea of this column of air above us that's creating this pressure. If you stake out a 1 meter square on the ground of the earth here, and you actually measure all the force from the weight of the weight of the atmosphere there, you can actually calculate the pressure, get 1.101 times 10 to the fifth Pascal, or you would get 1.01 times 10 to the fifth newtons of force spread across that area of 1 meter squared. So to calculate the average density, we would of course need to know the pressure and the height, and then G, of course. So we know the pressure at the surface of the earth is at, kind of an average pressure at the surface, which is 1.01 times 10 to the fifth newtons per meter squared. Divide that by the height of the atmosphere, which is about 120,000 meters, and divide it by G as well, and you get 8.59 times 10 to the minus 2 kilograms per meter cubed, which is about the density of nitrogen air-ish, nitrogen gas-ish on the earth. So that makes sense. So how deep do we have to get the same amount of pressure as we see in the atmosphere? So what we're going to do is we're going to set this equal to 1.01 and calculate the depth with water as our density here. So there's the water density. And it turns out it has to be 10.3 meters of water. You have to go 10.3 meters below the surface of the water to feel the same amount of pressure that you feel from the atmosphere. And that's assuming there's no atmosphere on top of the water. If any of you have ever been to 10.3 meters, you'll know kind of what that feels like. It's not very comfortable. 10.3 meters is like 35 feet deep or something. Ish. Somewhere in that range. It's pretty intense. 35 feet deep is difficult for most people to swim to. Most people would have a hard time holding their breath long enough to go that deep. And most people are very uncomfortable with that amount of pressure on their skull, on their lungs, and on their ears, on their eyes also. It becomes very, very uncomfortable, even going 20 feet deep, and let alone 35. I think the deepest I've ever been is about 40, but I was also a competitive swimmer and a pretty good free diver. So I spent a lot of my youth in the water and diving underwater in the ocean and other places. So I had a lot of experience, but 40 feet was difficult even for me. To go any deeper, comfortably for most people, you have to wear scuba gear. Scuba gear increases the pressure of the gas in your lungs so that it counteracts the pressure on your body. So it doesn't squeeze the air out of your lungs so easily. And then as you can go even deeper, you can increase that pressure and go even deeper. But as you come up, you have to decrease that pressure, because if you come out of the water with all that pressure inside your body, it can cause serious problems. The air tries to push out of your body in different ways. So, Pascal's principle. As I mentioned before, Pascal's principle is this idea where if you apply a pressure to one part of a fluid, it transmits. And it has some interesting implications. So here we have a system of fluid like water. And this works really only for, this works best. Excuse me. This works best in an ideal fluid. It works in other fluids as well, but ideal fluids are fluids where you have no compression. So when you push on it, it doesn't make it a smaller volume. It's not required, but it just works best for that. Here they put water inside of these tanks, and water doesn't compress very well, so it's pretty incompressible. So this will work quite well. And they've put this sealed movable thing they call a piston on each side. And as you push down on this piston here, no fluid escapes this system. But as you push down on it with some force, you create a pressure because your force is transmitted across the area onto this fluid, this area 1 here. So the pressure here is equal to force 1 divided by area 1. But because you've applied a pressure here, and by Pascal's principle, that pressure will transmit through the entire fluid everywhere. So that pressure will be the same everywhere in this fluid. So pressure 2 is equal to pressure 1 when you do this. But pressure 2 is equal to force 2, which is bigger, over area 2, which is bigger. And that's totally doable. You know, you know mathematically that you can have something that looks like this, a small force 1 over a small area, divided by a small area 1, can equal a big force 2 over a big area 2. A small number divided by a small number can equal a big number divided by a big number, but as long as there's, the right sizes are in here, as long as these things are you've got this proportionality thing going on. So that can happen. So pressure 1 can equal pressure 2. That can happen. But the funny thing is that you're putting a small force in here and you're getting a huge force out here. Well, that's useful. You can actually, push here with 1 pound and get out 10 pounds, or push here with 1 pound and get 100 pounds out. Well, that's always useful if you can do something that doesn't take much force and get something that gets a lot of force, right? These are advantageous machines that we use. And this is what we call hydraulics. The other thing that you can do is you can push down on the big one, and this one will move just a little bit, but a lot of fluid will move over here because of the big area here. And this one will move a lot. So if you move piston 2 just a little bit, you move piston 1 a lot. If you move piston 1 a little bit, you move piston 2 a lot in the opposite direction. So you have 2 different things here. You can go big force to small force to big force, or big force to small force, or you can go small movement to big movement, or big movement to small movement. And this is used in so many different ways in the real world. The most common one that it's used in is your brake system in your car. So the brake system in your car, you apply a small force at one place and you get a big force in another place. Where do you apply the small force in the brake system in your car? Can anyone guess where you apply a small force on the brake system in your car? Somebody's got to guess. Come on.
Can you repeat the question? My internet was cutting out there for a second.
So if this is the brake system in our car, there's a small force and a big force. What thing in our brake system in our car do we apply the small force to? And which thing gets the big force?
Would the brake pedal be like the small force, and then like the engine would be the small force or the big force?
Yeah, so on the pedal, there's a small piston behind your pedal. And it looks like this. Actually, I think they show us later here. Yeah, it looks like this. Behind your pedal, there's a small cylinder. And your pedal is connected to it. And when you push on your pedal, it pushes a piston into this small cylinder. In brake systems, this is called the master cylinder. And it's small. It's quite small. It's connected through some pipes. This fluid goes through these pipes and is connected to these big cylinders that are on your wheels. And this is an old-fashioned kind of car that has drum brakes. So you have these big shoes in here, and these pistons push these shoes outward, and they hit onto this drum that you're only seeing as a circle here. Nowadays, instead of having shoes and drums, you have these cantilevers, these kind of like pinchers that pinch a disc instead. But it's the same idea. You have small cylinder and big cylinder. You apply a small force here. I mean, the amount of force that you put here is maybe 100 newtons, maybe 200 newtons if you really slam on the brake. Not much. force here. Certainly not enough to lift you off the ground or something. But the amount of force on this end is so much bigger. And it has to be, because to stop your car, you need a lot of force. This has to be a huge amount of force. And so that's why they have the big cylinder. So this is the small cylinder, is called the master cylinder. These big ones are actually called the slave cylinders. And it's not very politically correct, but it does make sense to call them that, because, you know, if you're thinking about a master slave system, the master really doesn't do much of the work. And this cylinder doesn't do much. It doesn't have much force. It doesn't have much movement. Whereas the slaves do all of the work. It's a lot of force and a lot of movement. And that's the whole reason they call it the master slave cylinders, right? I don't know if anybody calls them that anymore. Probably not because of political correctness, but in the car world, they definitely use that terminology, master cylinder and slave cylinders. They probably have some new version of it now. I don't know what it is, but the analogy makes sense. This is the equation. The pressure is the same at the smaller cylinder and at the bigger cylinder, but the force at the smaller cylinder is smaller. The area is smaller. So this is small over small equals big over big. Well, what we're trying to do is calculate the size of the force at the big cylinder. So that's F2. We solve it for F2 and we get area 2 over area 1 times F1. Well, if we plug in the area of these cylinders, which are circular cylinders, it's pi r squared over pi r squared, r2 over r1. 1.25 centimeters is the radius of the big cylinder. 0.25 is the radius of the small cylinder. And then we have our 500 Newton force for the braking. So pushing on the brake, we're going to push with 500 Newtons this time. Plug all, plug all these into your calculator, you get 1.25 times 10 to the 4th Newtons. So that's 12,000 Newtons out from just 500 Newtons in. It's 100 times more, 50 times more. So that is the idea of hydraulics. Now, how to measure temperature. We're getting very close to the end. We don't have time to take a break with this chapter because it's got so much stuff in it. How to measure temperature. There are lots of different ways. You can measure two kinds of temperature, gauge pressure or absolute pressure. Gauge pressure is the pressure between two things. So you're essentially measuring how much something is above or below the pressure that you're living in or that you exist in. That's gauge pressure. So when we say a tire has 100 PSI, that's a gauge pressure. It's 100 PSI above the atmospheric pressure that we live in. Absolute pressure is just the absolute pressure above zero pressure. So the absolute pressure of the atmosphere is 1.01 times 10 to the 5th Pascal above zero pressure. Where zero pressure you could think of as being out in space where there's no atmosphere pushing on you and nothing really running into you, no forces acting on you. So what kind of devices do we use for this? This is one kind of device called an aneroid gauge. An aneroid gauge has this kind of place where where a fluid can come in and push on this bellows, right? This bellows, if you apply pressure to it, stretches. And the other end of the bellows is connected to this needle that can rotate around to different pressures. If there's no pressure here, this thing will rotate down to zero. So this can be used to measure absolute pressure. If there's absolutely zero pressure, it goes to zero. If any pressure is applied, then it will rotate as this thing gets squeezed. So this can be used to measure absolute pressure. It can also be used to measure gauge pressure. You can set up your scale up here. So let's say right here, this is atmospheric pressure. You can set up this scale to read zero atmospheric pressure. And then anything above that will go higher than that. Anything below it will go below it. So this aneroid gauge can be used to measure either atmospheric can be used to measure gauge pressure or absolute pressure, depending on how it's calibrated on the scale up here. This is what we call a manometer, an open tube manometer. It's just essentially a tube of glass or something that's see-through. It can be plastic, but it's just got a bend in it, and you fill it with a material. You fill it with a liquid of some kind. Usually, these are filled with mercury because mercury gives you a higher resolution at lower height. Well, it gives you better measurability, I guess. So you put these, you bend this tube like this, and then you connect one side of the tube to the thing that you want to measure the pressure. And so you're measuring the pressure in a balloon that's been blown up. So it's got a high pressure in the balloon, and that high pressure pushes on this liquid, and it raises the liquid because it lowers the right side, which raises the left side, right? And the difference in height can be used to calculate the pressure, right? You can measure the absolute pressure by taking the atmospheric pressure and adding this height times the rho times gravity. Or you can just measure the gauge pressure by taking this height and multiplying it by rho times gravity. So it can also measure absolute or gauge pressure, but only if you know the atmospheric pressure. You can also measure something low pressure. Here you have some vacuum packed peanuts, which has very little gas in it, so it's very low pressure. And that very low pressure pushes on this liquid, but the atmosphere presses on harder because the atmosphere is a higher pressure. So you end up getting a change in height the other way, but you still use the same equations, except that you're putting a minus sign in there because the internal pressure is greater than the atmospheric pressure. So that's an open tube manometer. And they actually use an open tube manometer to measure blood pressure. This is kind of the setup for blood pressure. What they do is they pump up this balloon with high pressure, and that balloon is connected to a cuff, which is, cutting off the blood in your arm. And as it cuts off the blood, they're listening to the blood flow. And once they get to a high enough pressure and that stops your blood from flowing, then they write that number down. And then they release the pressure. And as the pressure releases, they're listening to the blood flow in your arm. And as the blood flow starts to flow again, they write down the pressure where it starts flowing again. And those two numbers are your systolic and diastolic blood pressure. So, and it should be, between these two numbers to be kind of considered normal or healthy or whatever. And that's basically the idea. It's not usually a Mickey Mouse balloon. Usually it's that little black bulb or whatever. But that's how they do that. So the maximum called the systolic, the minimum called the diastolic. I don't know if I actually said it that way. I think I said it in that order, but I didn't make it clear necessarily. And here you can see that blood pressure cuff. This one seems like it's an automatic one because it doesn't have a bulb attached to it. So it's probably a machine that fills the blood pressure cuff with air and then releases it, and also probably listens to the heartbeat, but it works. You can also use the same idea to put blood in the body. So if you've got an IV solution and you're trying to put saline solution into the body, for example, the IV bag is placed above the arm, and they literally, in some cases they literally just watch the tube that's going into the arm. The tube that's going into the arm will appear like it's clear if the fluid is going into the arm, if the bag is high enough that it's creating a pressure. So the higher you lift the bag, the more height there is between the top of the fluid and the bottom of the fluid, and that creates more pressure at the entry point. But if the bag is too low, you will see blood in the tube because the blood pressure is higher than the pressure at the tube, and so the blood is leaving the body instead of liquid entering the body. And so if the blood is coming up the tube, then they know to lift the bag up a little bit higher. They can actually also increase the amount of fluid going in by raising up the bag higher or lower. Usually that's not so important. But if that is important, for example, if there are drugs in the fluid and they have to deliver those drugs at a certain rate into the bloodstream, which sometimes happens if you're dealing with really potent drugs, then they actually just put a pump on it to put that fluid at a specific pressure above your blood pressure. So they're measuring your blood pressure on one arm and delivering the fluid on the other arm so that they know exactly what pressure they want to enter it at, so that they know how much of the drug is going into your system at any given time. And sometimes that's necessary. Same with adding blood to the body. If they're actually putting in platelets or putting in red blood cells or something like that, they usually want to, sometimes they want to put it in a certain amount, especially if somebody's bleeding. They want to keep up with the bleeding by adding more blood at the same rate that the person is bleeding at. So they can use that as well. Here's another device for measuring pressure called the barometer, which I'm sure you've heard of. The barometer is essentially this long tube that's sealed off at one end and open at the other end, and you fill it with a liquid, and then you turn it over in a bowl of the same liquid without letting any liquid out of the tube. You fill this tube all the way to the top, and then you like put your thumb over it so nothing can escape, or you put a piece of like that, I don't know, put a cork in it or something so that nothing can come out. And then you turn it over into a bowl of liquid, and then you let it out. Then you uncork that or whatever. And what will happen is a bunch of this fluid will flow down into the bowl. And what you're left with up here is actually a vacuum. The air can't get up in there because there's no way for it to get in. It's a vacuum up there. What's happening here is that you have the weight of the fluid inside here pushing down, and you have the pressure from the atmosphere pushing on the fluid out here, which pushes up. And it balances at a particular height. Now, if this is water, the height is like 10 meters because water doesn't have much density to it. However, if it's mercury, which has much more density, then it's under 1 meter. It's less than 1 meter. It's about 700 millimeters or so. And that's what they use to measure pressure. They often use this height of mercury or millimeters of mercury to determine the pressure in your blood, for example. Sometimes they use millimeters of mercury. They also use millimeters of mercury in weather all the time. So this is another way of measuring pressure. And they actually have the conversions here for millimeters of mercury. They also have it for centimeters of water. But millimeters of mercury is right here, centimeters Hg, millimeters Hg. So 760 millimeters of mercury is 1 atmosphere. 1 atmosphere is 1.01 times 10 to the 5th newtons per meter, or 10 times 10 to the 5th pascals. So they have all these different conversions. And they're even showing more different units of pressure here. There's dynes per centimeter squared. That one's almost never used. But they have atmospheres. 1 atmosphere is 1 Pascal, essentially. Or sorry, is 1.01 times 10 to the 5th Pascal. So it's 1 atmosphere is this one up here, 1.013 times 10 to the 5th Pascal. 1 millimeter of mercury is equal to 133 pascals. So 1 bar or 1 millibar in pascals. They've got all these conversions. All right, Archimedes' principle. So this is really the last section of doing much calculation in this chapter. Archimedes was a natural philosopher a couple thousand years ago in Greece, and is particularly in Syracuse, which was kind of an independent city-state in the Grecian region, in the Greece region, the Andean region. And the king of Syracuse came to him one day and said, Archimedes, I gave like a kilogram of gold to my goldsmith. They didn't use kilograms back then, but he said, I gave some pure gold to my goldsmith and asked him to make me a crown. But I'm not sure if he gave me back a pure gold crown, because it's very easy to mix a little bit of silver with gold or a little bit of copper with gold and to make it still look like gold. So if you take out take out 50 grams or 100 grams of gold from a pure gold block and replace it with 100 grams of silver, you'll have a little bit more metal there because silver is not as dense as gold, but it will still look like gold. And it's very difficult to determine whether or not it's pure gold without melting it down. In fact, it's impossible in those days to figure it out. And he didn't want to melt his crown. He liked his crown. So the king came to Archimedes and said, is there a way of figuring out if my crown is still pure gold? And Archimedes thought about it and thought about it. And one day he was sitting in his bathtub, as the story goes, and he put his arms down in the water and noticed something about the level of the water in his bathtub. What happens if you're sitting in your bathtub and you sink your arms below the water? What happens to the level of the water in the bathtub?
It rises.
It rises. So he noticed that. And he noticed one other thing. He noticed something about the weight of his arms. Before he put his arms in the water, his arms had a particular weight. But after he put his arms in the water, they weighed less. They felt less heavy. In fact, the water was kind of holding them up. His arms were floating on the water. There was some kind of force that was preventing his arms from being pushed under the water. And if he pushed them all the way under, the water went up. And so he's trying to figure out what the relationship is here. And then it dawned on him. He figured it out. And he jumped out of the bathtub and he ran through the streets of Syracuse completely naked, yelling, Eureka, which means I have found it. I've figured it out. And that's how the story goes. So if you go on to Google and you search for Archimedes, this is what you find. You see things like this. They have even better ones. But Archimedes, there's maybe you have to search for Eureka. I can't remember. But there's actually even tubs that are made to commemorate this. There we go, Eureka. Here we go, the true story of Eureka. Anyway, that is Archimedes. What he'd figured out is that when you put something under the water, it displaces the fluid. It moves the fluid. The fluid goes up. It has nowhere else to go. Eventually it'll hit the ends of whatever's containing the fluid and go up, right? And so as that fluid goes up, it's higher in the gravitational field. And so it creates more pressure underneath it. That more pressure underneath it lifts whatever's underneath it. And if your arms are the things that cause that fluid to go up, your arms will feel some force underneath them. And so they will be pressed, they will be forced upward by the force caused by the raised liquid. And he actually figured it out. He actually figured out that the amount of fluid that goes up, the weight of the fluid that gets lifted up, is equal to the amount of force that your arms feel by pushing that water up. So the weight of the water displaced is equal to the amount of force holding your arms up or pushing up on your arms. We call that the buoyant force. And here they're showing this by showing a difference in the force in the bottom and the top of a piece of water in the fluid. I find that confusing, but that's fine, whatever. The force that holds up an object in a fluid, because it has displaced that fluid, is what we call the buoyant force. And the buoyant force is equal to the weight of the water that it is displaced, or the weight of the fluid that it is displaced. It's even true in air. We just don't experience it in air as much, so we don't think about it as much. But if you're a hot air balloon floats because you take some air and put it inside of a big sack, and then you heat up the air in that sack so that the air becomes warm. As the air becomes warmer, it expands and leaves the sack. The sack actually has an open hole at the bottom, and sometimes even at the top, that allows air to leave the balloon so that you have less and less air inside the sack, but it's still taking up the same amount of space because it's hotter and it's moving more. And that big sack of air actually is displacing more weight of air than the weight of the balloon. So it has more buoyant force up than it has weight down. and the balloon floats because of that. It's true of all things that float in liquids and all things that float um, uh, in in gases. The buoyant force is equal to the weight of the fluid displaced by the object that is feeling the buoyant force. So what is the weight of that fluid? The weight of that fluid is going to be equal to the mass of that fluid times gravity, or the density of that fluid times the volume of that fluid times gravity, one or the other. So here we have an example of we have a buoyant force of a piece of steel, just a big chunk of solid steel that has a mass of 1 times 10 to the 7 kilograms. And we're just going to put it completely underwater. Now, is something like a chunk of steel, does it feel a buoyant force underwater? Well, how do you tell? Well, you put it underwater and drop it, and then you put it in air and drop it and compare. When you drop something in water that is going to sink in water, and then you drop that same thing in air, in which place does it drop with the most acceleration? Does it drop the most acceleration in air or water? Let's take, for example, a bowling ball. If you drop a bowling ball in water and then you drop the same bowling ball in air, which one does it drop faster in, the air or the water?
The air.
The air. In other words, in air, the buoyant force is much less. Here's our bowling ball in air. It has gravity pulling it this way with a big force. And it has a buoyant force from the displaced air. It's displacing this small amount of air, but that amount of air doesn't weigh very much. So the buoyant force is very small because the buoyant force is equal to the weight of the displaced air. But when that same buoyant force is in water, that much water weighs much more. So it has a bigger buoyant force. And that slows down the ball because it has a bigger buoyant force to counteract the gravitational force. If you tried to drop this through melted lead has an extreme amount of density, much more dense than a bowling ball. So the buoyant force is going to look like that. What's a bowling ball going to do if you drop it in molten lead? You have this big force going up and a much smaller force from the weight of the bowling ball going down. This is how much weight is displaced in this much lead. This much lead has this much weight pointing the other direction. So that's the buoyant force. So if you have a buoyant force going up that is much bigger than your weight going down, is this bowling ball going to sink? No, it's going to bob on the top. It won't even sink a little bit. It'll only have to displace a tiny bit of lead for these things to be equal, right? And this is actually why certain things float on the top of the water and certain things float somewhere in the middle of the water. A bowling ball floating on lead would float very close to, would float mostly out of the water. The level of the water would be like here, because this much volume of lead has the same weight as the ball. And so the upward buoyant force would equal the downward weight of the ball, right? But if I dropped a lead brick into boiling lead, a lead brick is only slightly more dense than liquid lead. So a lead brick would fall in and float probably below the surface right here, where the density, so the weight of the brick is like that, and the weight of the lead that it has displaced is the same. So it cancels out and floats down underneath the liquid a little bit. But if I drop in a tungsten brick, tungsten has more density. So if my brick is made of tungsten, then the mass of the tungsten brick is bigger. The weight of the tungsten brick, rather, is bigger than the weight of the lead that it's displaced. This much lead actually weighs less, so the buoyant force which is equal to the weight of the displaced lead, is less than the weight of the tungsten, so it will sink. It won't sink fast because they're pretty close, but it will sink. Slowly it will sink down into that molten lead. So let's calculate this buoyancy of this piece of steel. Well, you need to know the weight of the steel, or sorry, you need to know the weight of the water displaced. So you need to know how much volume is in this chunk of steel. Well, we know the density and we know the mass, so we can calculate the volume because density equals volume divided by, or mass divided by volume. So they do that. They take the mass of the steel that's given, they take the density of the steel from the chart on a couple of sections before, and this is how much volume that steel takes up. Then you use that volume to calculate the weight of the water displaced. This volume times the density of water, which is right here. This is the density of water. That's the volume of the steel that's displacing the water. That tells us how much weight, how much mass is displaced in water. That's the amount of mass displaced by water. Then to get the weight of that, you multiply by G right here. The weight of the water displaced is 1.3 times 10 to the 7 newtons. So that's 1.3, that's 13 million newtons of water displaced by that big chunk of steel. Well, the weight of the steel is actually much bigger than that. The weight of the steel is 9.8 times 10 to the 7. So this is like 1/6 the weight of the steel. So the steel is definitely going to fall. You have your chunk of steel. I'll give it some shading here. You have your chunk of steel. You have the weight of the chunk of steel. And you have the weight of the water displaced, about 1/6 of that. So it's definitely going to go down. The force down 6 times greater than the force up. It's going to accelerate down. It's going to fall. What if we change the shape of that steel so that something different happens? What if we turn it into a great big box that's hollow on the inside? So now the steel, the same amount of steel, but it's only in this red stripe. In the red line is the only part that has the steel. Inside here is just air, which pretty much has very little weight compared to the steel. So inside is just nothing, essentially. This, you have all this steel around here, and you seal it up into a great big box so that nothing can get inside of it. And then you put it in the water, right? Push it all the way under the water so that you have water completely surrounding it. Well, that's going to displace a lot more water because this is a much bigger box. All this steel has been stretched out from this tiny little box that was solid steel into this huge hollow steel box. Now it's displacing far more water, and the buoyant force is equal to the weight of the displaced water, right? And the weight of the displaced water is equal to the volume of the displaced water times the density of the displaced water. And this volume just got huge when we stretched this out and made this big sealed up box. So the buoyant force is now going to be huge because the density of water doesn't change. It's still the same. This buoyant force is now going to be huge. And it can be much bigger than the weight of the steel. So you can end up with a buoyant force like this and a weight like this. Well, this is what we call a boat. You make a great big box out of steel that's filled mostly with air. And now you have this huge buoyant force. And you can fill this thing up with stuff until the weight of the boat is just a little bit smaller than the buoyant force. And then you can take it across the ocean and you can unload it. And then you can load it up and take it back across the ocean, right? And this is what we call container ships. Let's see, actually, I think there's actually a good picture in this section of a container ship. Yeah, I had a good drawing anyway. So container ships our big hollow, big hollow hull, and you just fill them with stuff, right? Or oil rigs. Oil rigs or not oil rigs, but oil ships are the same way. They're just big hollow things, and they just fill them up with oil. Well, as they get more and more mass in them, they get heavier and heavier and heavier. They actually sink down in the water, and because that's how they displace more water to get more buoyant force. When they're empty, they're like this. They have very little of the ship is underwater, and they actually paint a line on the ship so that they know when it's full. The red line on those container ships tells you how full they are. This one's not full at all. You can keep filling it until the water reaches that line, and then you don't fill it anymore. That's the maximum for safety, right? Loaded ship, that line is completely under the water. You don't see it, right? And the reason that it floats higher is because the buoyant force and the weight of the ship are canceling each other out with just a little bit of displacement. That's all the water it has to move to equal the weight of this ship. But when you fill it up more, you have to displace more water. So it has to sink lower and displace more water to get bigger buoyant force, right? We often define something with objects that are floating with a specific gravity, particularly when it's floating in water. You take the density of the object, the average density of the object, divide it by the density of water, and you get its specific gravity. And the specific gravity essentially tells you how much something is going to float. So if you have a specific gravity that is less than 1, it's going to float. If it's greater than 1, it's going to sink. And the farther you are from 1, the more it's going to sink or float. So the smaller it is, the more it's going to float. The bigger it is away from 1, the more it's going to sink. And that's used often. That's used in chemistry a lot. It's used in a lot of different ways. So here we're going to actually calculate the density. We're going to calculate the average density of a floating woman. Apparently, 60 kilogram woman floats in freshwater with 97% of her volume submerged. Well, the fraction submerged is actually equal to the specific gravity, but you have to turn the percentage into a decimal. So 97% would be 0.97 for the fraction submerged, and that would be your density, your specific density essentially. So they're going to solve for the density of the person, and that would equal the fraction submerged as a decimal, 0.97 in this case, times the density of the fluid, which would be water. And so they go ahead and do that, and they find out that the density is 970 kilograms per meter cubed. They actually use this a lot in sports to essentially measure fat content in the body. So they will put an athlete in a chair and then weigh them. They'll weigh them outside of the water, they'll weigh them inside of the water, and calculate the percentage of their body fat and so on and so forth. But this is actually how Archimedes determined whether or not the crown of the king of Syracuse was actually gold or not. What he did is he measured the mass of the crown in air, which was the exact mass it should have been. If the king gave the goldsmith a kilogram of gold, then it would be equal to a kilogram right here. Then he put the crown underwater and did the mass again, measured the mass again. When you do this, the weight of the gold on the left side is going to change because of the buoyant force. The buoyant force in air is very small, so it doesn't really calculate in here. But the buoyant force in water is much more significant because water is so much more dense than air. So in this one, this particular side of this balance is going to get pushed up a little bit by the buoyant force. And that's going to depend on how much volume this thing displaces. So how much material is actually there. If it was the original amount of gold, then it'll be one number. But if it had silver mixed in, silver takes up more space than gold because gold is more dense. So it'll be a bigger volume and it'll be a bigger buoyant force. And you can actually calculate the apparent weight loss by the weight of the fluid displaced. So the apparent weight loss, or the difference between these two things times G, will give you the weight of the fluid displaced. And that weight of fluid displaced can be used to calculate the actual density of the metal of the crown. So we do that in this example. We do it with a Greek coin. The Greek coin is 8.630 grams, but we submerge it in water and find out that it loses some mass. It has a mass of 7.8 grams in water. So we're going to calculate the density of the gold by using this ratio or this equation that determines this, right? So the volume of the water is the mass of the water divided by the density of the water. And we're talking about the volume of the water displaced and the mass of the water displaced, right? By the coin or the crown or whatever else. But the change in that mass, which is that mass displaced, is the mass in air minus the mass in water. So we take the mass in air minus the mass in water, 0.830 grams, that is our mass of water displaced. So we plug that into our equation for mass of water. We know the density of water. So this is the volume that is displaced by that, 0.830 centimeters cubed. Now we know the mass that was displaced, and we know the volume that was, we know the mass of the coin, and we know the volume displaced by the coin. So we know the volume of the coin. So we can take the mass of the coin divided by the volume of the coin and get 10.4 grams per centimeters cubed. This is the density of silver, very close to it. So that coin would be silver. If we found this to be closer to the density of gold, which is like 18, then we could say it's pure. But if it's not exactly the density of gold, then we can actually figure out how much silver was mixed in as well. If the density of gold is 19, I think, or something like that, grams per centimeter cubed, and it comes in at 18.1, well, that's enough difference to think that some silver was mixed in. And you can calculate how much by calculating how much volume it should have been, and then figure out how much volume of silver they mixed in. And it turns out that Archimedes discovered that the goldsmith had mixed in some silver, and the goldsmith lost his head. So anyway, that is Archimedes' principle. Cohesion and adhesion in liquids is this idea that there are forces between molecules in liquids. Some of those forces are stronger than others. Water has a fairly strong force, but glycerin is even stronger. The bubble solutions are made with glycerin, and that's why they stick together and make those bubbles. Surface tension on fluids is also because of these forces between the molecules in the fluid. This is why certain bugs can walk across water. This is also why you can make very, very small objects float in water, even though they're more dense than water, because the surface tension from those molecules is actually strong enough to hold up very small things. And they talk about some particular equations with this. I don't think I give you any questions about this. It's interesting stuff, but the math is actually much more complex than they're making it here. And it's not, I don't think, very interesting to talk about these things without really understanding why they work. It's a much more advanced topic than they're making it here. But essentially, the higher the surface tension, the more forces there are to let's see. Do I have that right? Yeah, the higher the surface tension, the more forces there are to prevent you to keep things afloat or to push on things, I guess you can say. So mercury has a very high surface tension. Water is pretty good. Water's pretty high. Glycerin's high. Fluids in our body, in our tissues, blood is pretty high. Plasma, gold, quite high. Helium, very low. So, I mean, that's surface tension is present in so many different things, biologically, chemically, just in the universe in general. But the math is much more complicated than they're making it sound. So I don't go to it in a lot of detail. But it is one of the reasons that we get wet, actually. The reasons that water sticks to us is because of those intermolecular bonds and intermolecular forces between the things. You know, if you spill pure alcohol on you, you don't really get wet so much as you feel it evaporate off you very quickly. Or gasoline, you know, doesn't stay on your hand very long and runs off your hand very quickly and then evaporates super quickly because it doesn't have nearly the same amount of bonds on in them. It's also the reason for capillary action, the reason that things are sucked up tubes very quickly or between walls and things like this. It's the same idea. But anyway, they talk about a lot of this. They do a lot of calculations. This is how trees pull water up through the trunk, and plants, how they pull them up through their stems. They use this capillary action, and it has to do with these intermolecular bonds and so on. But like I said, I don't go to it in great detail in the homework, so you don't have to worry about it that much. Don't have to worry about it at all. I don't think I do anything in the homework like that, but I could be wrong, but I don't think I do. This section on blood pressure or pressures in the body, they're just talking about different pressures in different organs and different parts of your body. They talk about blood pressure in a little more detail, but it's not really anything different. It's still H times rho times G. So it's nothing really different. They do talk about, you know, the system of your blood in general. It requires that there's pressure in there to keep things moving. The blood pressure also keeps your veins and your arteries open. The reason that you can have blood flow through your arteries and your veins is that they're kept open by the blood pressure in your system. If you have too little blood pressure, you actually can have not enough pressure to hold them open so that they'll collapse. And that happens with stroke. When you have too little of blood pressure, you have a stroke when too little of a blood pressure causes, see if they show that. They don't really show that. But when you have very low blood pressure, it causes a stroke, and they actually show that, I think, in the next chapter. But you say, well, wait a second, strokes happen when people measure high blood pressure. Well, they measure high blood pressure in one region where the blood has slowed down, and it's low blood pressure where the blood speeds up. So where the blood is, where they're measuring the low blood pressure is not easy to measure because it only happens usually in very small parts of the blood vessel. The high blood pressure happens where it backs up in other places. And so that's much easier to measure. But it's still where the blood pressure goes low is where the stroke actually happens, and the blood vessel collapses and stops the blood from flowing altogether. But you can have the same problems as a stroke from low blood pressure. I once had a low blood pressure where I just about passed out because blood wasn't flowing through my system and wasn't getting up into my brain, which is really the same thing that causes problems with strokes. You stop this blood flow from a collapsed vein or a collapsed artery usually, and then that blood doesn't get up to your brain. So it's the same thing can happen. You can have the same problems with low blood pressure and high blood pressure measured by your doctor, but it's still caused by the same thing, by a stoppage of blood flow. It doesn't matter which way it actually is measured. And that is the end of the chapter. So we're done. Go ahead and get started on the homework. And we're going to go ahead and try to get that homework done by Wednesday. Then we'll answer questions tomorrow and Wednesday on the homework. And then I'm going to try to connect with you and do the next chapter starting Wednesday. I won't make it due Wednesday, but I want you to get it done and answer so I can get all your questions answered before we start the next chapter. I don't necessarily want to force you to get homework done all tomorrow and today or whatever, but try to get as much of it done as possible so you can ask your questions tomorrow and Wednesday. Any questions about any of that?
Yeah, thanks for recording it. And did I miss like any lab or anything like that I should write down?
No, we didn't talk about any labs today. I don't have a lab designed for this one.
Okay.
The IO lab does have a pressure sensor on it, but I haven't designed a lab for it yet. I don't know if anybody else has either. I probably will do one for the next chapter, so stay tuned for that. All right.
Okay, got it. Thank you.
Any
You
other questions?
mentioned that there was a test this week. When will that be due?
Is that on the calendar? I can't remember. Let's take a look here. So it looks like it's due Thursday. Yeah, if you need it due Friday or Saturday, that's fine too. But it looks like right now it's due Thursday at 5 p.m. But that can be moved if it needs to be.
Do you mind moving that to Friday? I was gonna do it at the library Thursday or Friday, just depending.
That's totally right. I'll move it right now.
Awesome. Thank
Be
you very
aware
much.
that they change, their hours are different on Friday. And you need to make sure that you make an appointment, because like a week ago, I had a student go in to take a test on Friday, and the successor just decided to close early and not tell anybody, and he hadn't made an appointment. So you got to make sure that you make an appointment at least a few days in advance so that they know to be there, even though they're supposed to be there. So just be aware of that.
Thanks.
Any other questions?
I don't know if I'll be able to get it done by Friday, since I'm getting some oral surgery done this week. What do you want me to do with that?
Well, we can move it to another day. I mean, how long do you think you'll need to get your surgery and recovery done?
I should be fine by like next week.
Okay. When are you having your surgery?
On Thursday.
Can you do it before your surgery? Can you do it Wednesday?
I would have to look at my work schedule.
Well, I would recommend to try to do it before. I just don't want to push you off so that you have a bunch of stuff next week, because we're here at the end of the semester. But if we have to open up next week for you, that's fine. That's doable. Sound
Thank
good?
you.
All right. All right. Have a good. Any other questions before we close up? We good to go?
Yeah, when would that recording be finished uploading? Or I don't know how
I
long.
will
it usually-
upload it today. I should have time to, the Zoom, whenever I do this recording with Zoom takes a little bit of time to convert it. And sometimes I forget to stay around long enough for it to convert, so I don't upload it right away, but I should be able to stay here long enough for it to upload so that we can get that done today.
Okay, awesome. Thank you, sir.
Any other questions? All right. Have a great couple of days. We'll see you Wednesday. I will be connecting from a remote location, so hopefully I will be able to connect well. We'll see how that works out. And I will see you later.
We'll see you, sir. Have fun.